Hey, welcome to video 3, part 2, where we discussed the neutralization reactions. We just took a look at an example of a strong acid and a strong base reacting to undergo a neutralization, in essence, to form liquid water as their resulting products of their double displacement. Here we are going to look again at a neutralization reaction, the only difference being we are now looking at a weak acid with a strong base and seeing how that might change how we would write these complete molecular and net ionic equations. So let's pick acetic acid. That is not one of our 6 strong acids. And how about potassium hydroxide as our strong base? Now again, if we were going to think about the Arrhenius definition only, the potassium hydroxide, that's going to contribute hydroxide ions to solution. This is what's going to make it the base. Whereas the acetic acid, that's going to contribute that acidic proton to solution, so that makes it an acid. And if we want to prove this to ourselves, let's go ahead and show what these things might generate in solution in order to create either acidic or basic particles, meaning hydrogen ions or hydroxide ions in solution. So for acetic acid, I do in fact generate the acetate ion and the acidic H+. However, we know that this is a partial dissociation. And because this overall is a partial dissociation, then I have to write my actual neutralization reaction as being one that is partial as well, meaning I can show that the neutralization does occur in the forward direction where I have some acid donating a proton to my base which accepts it, but then I have to take into account the fact that my acid does not always have that H plus available to donate because it's in this state of equilibrium between being separated into its H plus and acetate versus not. So anytime we're looking at weak reactions, we are always going to use this kind of double arrow notation just to indicate that we are fully well aware that we've got weak or partial dissociation here for our species, whether it's a weak acid or a weak base. But let's continue writing our ions for base. And since this is our acid, this is going to donate to the base. This is what makes us our Bronsted-Lowry acid and base. So if I undergo my double displacement, I should see the formation of HOH. And then I've got potassium and then my acetate, which again, these come together in a 1-to-1 manner. So I form HOH liquid and potassium acetate, which is a soluble compound. If you need to verify that, check your solubility rules. So let's rewrite our molecular equation, making sure that we are fully balanced. So looking over here, I've got one acetate, one H plus, one potassium, one hydroxide, one hydroxide. Excellent. This means my balancing is not too difficult. So I've got CH3COOH, my acetic acid, reacting with my strong potassium hydroxide base. Since this is a weak strong interaction, or it at least involves a thing that partially dissociates, I need to indicate that with this double arrow. This is going to form H2O liquid and then potassium acetate. If I wanted to do my complete ionic equation, I would show everything that is aqueous dissociated Now, the thing about this is because we only have partial dissociation, it's actually more correct to leave this in its undissociated form. Just because it's better to imply that there's more coupling than it is to imply a perfect dissociation, which would make this thing a strong acid, which we know it isn't. So I'm going to keep all weak species in their molecular form, meaning undissociated. And because I'm using this double arrow, that will also be a signifier to whoever's reading my chemical equation that, okay, yes, we've got some kind of weak species that shows a partial reaction or partial dissociation somewhere in our equation. But potassium hydroxide, that's a strong base, so I can certainly separate that into its ions. That will become an electrolyte. This forms H2O liquid, potassium ion, and then acetate anion. So this is my complete ionic equation. And now for my net ionic equation, I will have my acetic acid because again, I am leaving this in its undissociated form to signify that we are aware that this is a weak species. Looks like my only spectator ion then is my potassium ion. So I have acetic acid reacting with my hydroxide anion in some kind of partial manner to create H2O, and then the acetate anion. But ultimately, if I think about what's going on here, I still had an H with an OH come together to make H2O. We're just implying that we recognize that that H is wrapped up in this imperfect dissociation with its acetate anion because it is a weak acid. So this is how you would do something like a complete and net ionic equation writing for a neutralization reaction that involves something that dissociates partially. So we'll probably see some examples of weakly dissociating bases probably on Wednesday. We'll start with a warm-up there. And that is neutralization reactions. Acid plus base yields salt and water. All right. So up next, we have acidity and basicity of solutions. I think I'm actually going to save this for Wednesday. The fifth, so we will talk about acidity, basicity, pH, pOH, where these things come from, how we can calculate it, and then we will finish up aqueous reactions, especially the classes of aqueous reactions with oxidation reduction reactions on Friday. And then from there, we will move into something called stoichiometry, which we've seen already. It means mole counting, coming up next week. So I will see you all tomorrow for midterm number 2. Good luck.